have a nice talk from Steve Dalby. He's going to be talking about streamlining content discovery. There will be no Q&A because we'd rather have you decompress with a beverage. If you do have questions, please go grab a beverage with Steve. He's great. So thanks so much for sticking out with us. We will have the QR code. Please, again, take a few minutes to give us feedback. This is how we learn to get better, and thank you, and feedback is a gift. Just before I forget, after this, again, it's going to be happy hour on this floor. This floor, so don't go anywhere. The drinks are coming to you. Without further ado, Steve Dalby.
Thanks, Alex.
You're welcome.
So last session of the day. I hope you've had a good time. Right, so my name's Steve. I work in our industry solutions team. So we have the pleasure of taking a lot of the products and features that our product and engineering teams are building and working out how to use them to solve industry-specific challenges. So today we're going to talk a little bit about content discovery. So I figure a reasonable place to start with this is, what do I mean when I talk about content discovery? So back when I started, in the industry, many years ago now, largely the way in which you would go about ensuring that you got the right content in front of the right users at the right time, it was largely a question of sort of user experience. How well could you, build the navigation on your websites and taxonomies and whatnot? Today, though, that is no longer enough. The volumes of content available on most services, if you think of streaming services, for example, or modern e-commerce platforms, we need to do, a lot better than that. So there are largely two technologies at play here. One is search. So if you go to some kind of service or a site and you know roughly what it is that you're interested in, then you need to use the powerful search functionality in order to be able to locate the thing that you're searching for. The alternative is, maybe I don't quite know what I want. Often, like if you go to Netflix, you just want to watch something, for example, you're not quite sure what. You're relying upon that site having powerful recommendations functionality to recommend you something that will be relevant and something which you're going to like. So a couple of examples. Netflix. Now, if you look at Netflix, there's a pretty good example. Netflix have, as of sort of January this year-ish, about 37,000 hours of original content hosted on their site. Now, interestingly with Netflix, they state that over 80% of all content interactions originate from their recommendations engine. And if you look at on the screen there, each of those rows is completely personalized to me. Each rows are displayed as personalized, the ordering is personalized, and this is really part of the competitive differentiation in modern streaming sites. Now, Netflix is interesting, but the content, although there's lots of content, it's not changing that frequently. Take another example though, YouTube. Now, if you look at YouTube, over 500 hours of content uploaded to YouTube every single minute. So that gives a pretty unique challenge. How do you get that content reflected in your recommendation and search results quickly? But it's not just media. If we take a look at everyone's favorite e-commerce sites, Amazon.com. Amazon.com, 12 million products on Amazon.com. That's if you exclude the marketplace stuff. If you include marketplace, that balloons to 350 million products. Again, how do you get the right products in front of the right users at the right time? And that's where, again, search and recommendations come to the front. And it's not just anecdotal evidence. McKinsey have done some research on this. They've been able to correlate, organizations that do well at this stuff, that excel at personalization, to directly generating more revenue than others. So this is something which is definitely top of mind for many organizations. So for the rest of the talk, I'm going to talk a little bit about, if you've got you're looking after some service, how can you go about improving or adding this sort of functionality into it? So let's start by assuming that we have an application. Typical sort of application, I've got a number of channels by which you'd interact with that service. we have a bunch of microservices sat in the middle, and then we have a database at the back, MongoDB in this instance. So let's start with search. I want to add search in. How do I do it? Well, there are plenty of options out there. I pick one. So a few examples that we see pretty often there. There's obviously the open source Lucene project, which underpins both Solr and Elastic. The cloud services have their own offerings as well. And it becomes an integration challenge. I take one of those products, and I need to integrate it into my architecture. But guess what? That integration is down to the developer to figure out. To make sure that the data reflected in my search engine is consistent with the data that's relevant there in my database. If I look at recommendations, it gets even more complicated. And this is a diagram here taken off of Amazon's website. I could have taken one off of any of the cloud providers. Everybody has one of these. They have their Amazon personalized service. But if you look at the service itself, obviously in the bottom left-hand corner there is a lot of different components that need to be wired together in order to make this work. And this is a perfectly good architecture, but again, you as an organization are responsible for spinning all this up, getting it all working together, all of the security that goes along with that, and then guess what? Again, integrating that with the rest of your application. So this is definitely a non-trivial challenge. So what I'm going to do is I'm going to look at search and recommendations one at a time. A lot has been said about search already today, so I'm going to spend a little less time on that and a bit more time on the recommendation side of things. Look at search. So if we look at some of the common features that are going to be that are required from a search engine, things such as fuzzy search. So you type something in, you make a spelling mistake, you still expect results to come back. Syntax highlighting, so we can highlight relevant search terms, different weighting and scoring algorithms. Now these are very different challenges to those that are solved by databases, and I include MongoDB in this. Very different challenge. And this is why search engines are of course so prevalent in modern architectures. So how is search usually built? Well, as I alluded to earlier, you have your database cluster, you have your search engine, whichever one you happen to have chosen. You have some data synchronization in the middle. Then from the application perspective, then I need to know, am I issuing a search query or am I issuing a database query? Do I need to join the results somewhere inside of my application? And this is troublesome, right? I mean, if you're a developer, you've got multiple different languages that you're needing to learn how to deal with here. You need to worry about being able to join those results in the application, for example. Not that it's all necessarily massively hard, but it's time you could be better spent doing something else. Architecturally, it's more complex, particularly when you're looking at the operations side of things. You've got the data synchronization to manage. You've got to keep those things in sync. And then there's the operational overhead. The ops team now have to provision different systems. They've got to secure, they've got to upgrade, the backup, the monitoring, all of this stuff that often gets forgotten about, you need to be thinking about here. And this is really why we have Atlas search. It's the architectural diagram up there for that. So that as a end user, I can interact with my data using one API, use the dollar search operator there. You don't need to worry about hosting the separate the two separate technologies. All of that is abstracted and handled behind the scenes. But of course, if you listened this morning, search is getting smarter now. So vector search. So no longer is it enough to just be returning results for the search terms that you actually type in. We also want to be able to return results for results that are similar to what I typed in. For example, on the screen there, if you search for kitten, well, a cat is very similar to a kitten, so I probably want to get results for that as well. And before vector search, how would I have done this? Well, I'd have had to go through a laborious, exercise of defining a whole set of synonyms, for example, that for my search engine. Okay, if I've only got a very narrow domain, but if you're looking at something which is much broader, like e-commerce or the streaming media side of things, that's quickly going to become just simply impractical. So this is going to be really important in these sorts of systems. So that's really what I wanted to talk about in terms of search. I want to move on to recommendations engines. So let's look to start with about what do I mean by a recommendations engine. Well, so first of all, we start with some input data. And this input data, I borrowed this from Netflix's developer blog, which is always a good source of information there. So, what are they capturing? Well, they're capturing, what are other people doing on the sites? What am I doing on the site? So what have I watched previously? What have I liked previously? They're capturing data specific to the actual titles themselves, the genre, the director, the actors, etc. They're also capturing more interesting stuff, like what device am I watching on? Am I watching on my phone, my TV, a tablet? And what time of day is it? Am I more likely to be doing something for work at this time, or am I likely to be sat at home, like watching something in the evening? All this plays into these decisions. And this obviously goes into a recommendations engine. And this is really, I guess, where the smart stuff starts to happen. There's sort of, broadly speaking, two main categories of algorithms here. We've got collaborative filtering. You can think about that a little bit of like crowdsourcing. Like what did other people do that are identified as being in a similar cohort to me? Then there's content-based filtering, which is based on the things that I like and the metadata for other content I've got out there. Then come up with a recommendation. And there's a whole bunch of hybrids in there as well. The output, of course, as you might expect, is a user-specific set of recommendations, typically sort of key value type setup, which can then be consumed by my application when I'm presenting maybe like a homepage, for example, or a set of search results. So let's look at the different sort of how this fits together. A couple of different approaches here. So the most simplest approach is I could say, well, I'm going to do this based on in a batch. So I'm going to have my application. It's going to be generating some telemetry data. That's going to go into some database, for example, and then periodically, could be every few hours or every once a day, whatever it's going to be, some batch job's going to run. It's going to generate some recommendations for all of the users that I know about at that time, and they're then going to be made available to my application to be able to go and issue queries against. Now that's got there's some benefits and some drawbacks to that. Of course, the recommendations are static at that point, until such a time as that thing runs again, and these things get updated. And probably more important though is that I can be less responsive to what a user is doing at that particular moment in time. If you're searching for, a specific thing, and the recommendations engine can't really pick up on that, so it's only going to give you a static set of recommendations. However, from a computational perspective, it's lower. There's economies of scale at play here, so you can do this, arguably more efficiently from a resource perspective. What's the alternative? Well, the alternative is that I have a bit more of a hybrid, where I probably still am going to have this batch where I'm capturing some of the slower changing things, such as my user demographic data, but I also need to add a real-time stream into here as well. So I can capture telemetry data coming directly from the application and make that immediately available to the recommendation service in generating a set of recommendations. At this point, we can be much more adaptable to what the user is doing at that particular time. What are they trying to achieve? We can minimize what's referred to as a cold start problem. So that's a new person who signs up. We don't know anything about them, so they get a very generic experience until such a time as we learn some information about them. With this, we can minimize and shrink that time down considerably. And finally, on the other side of that, computationally, operationally, there's more moving parts. It is slightly more complex on that side of things. That's the trade-off to think about here. So let's think about this, as to what this means from a data perspective. So as with all machine learning models at the top there, we need a large amount of historical data. We need to be able to train this model based on historic data. So we take that data, we need to go and process that, we need to train our model, and at the bottom we have sort of the more of the real-time feed, taking the live data coming in, that live telemetry data, and then feeding that and processing that. So examples of some queries. At the top there, for example, get me all of the data about all of like the movies that I have in my database. I'm using the example here of the streaming media. Or get me all the information I have about all of the users that I have in the system in terms of what they like, what they don't like, what they've watched, what they've not watched. It's very much a very analytical sort of query. It is a sort of query which would very often have fallen to the sort of data warehouses of the world. On the other side, on the live data side, we're looking at what's a user searching for right now in this instance, or what have they just sort of clicked watch, or what have they just hit sort of that they liked, or if there is a recommendation that's been generated, I want to store that and make it available so that some microservice can just say, go and get me the recommendations for Steve and display that on the front end. So what we're sort of describing here is at the top an analytical data plane, and at the bottom more of a transactional or operational plane. And if you listen to a few of the talks earlier on, this is where we're saying, well, rather than looking at bringing multiple different technologies into there, what if we could do this all from within one data platform, as in this case, MongoDB. So let's look for a moment at MongoDB's role in a machine learning pipeline. So what are we doing here? So we're ingesting a bunch of raw data from a whole bunch of potentially different sources. We then need to go through a period of feature preparation, and I'm going to go into a bit more of this in each of these steps in a bit more detail going on. That's making that data a bit more usable. I then need to train my model, train the coefficients so that we can actually generate meaningful recommendations. We've got to serve our model, and then there is obviously the model monitoring to look for drift that may well occur over time. And then once we have generated any insights, we want to persist them somewhere, as I mentioned, so we can serve those up. So where does MongoDB fit here? Well, if you're expecting me to say that this can all be done inside of MongoDB, then sorry, that's not the story here. MongoDB very much sits on the left-hand side of this picture. So a lot of the data ingestion, the feature preparation, and then where the intersection is where we start talking about model training, which is really where an MLOps or AI ML platform, Databricks, SageMaker, there's a whole bunch of them out there, start coming into play. And for us, it's really around the integration point there. How do we integrate with those different platforms? So, sticking to those in a bit more detail. So, if I look at the raw data ingestion, it's clear that I'm going to need data from a large variety of different places, ranging from, as I said, the metadata, core data about my users. There could be promotional data. There's telemetry data in terms of like search history, content interaction. So what are people watching and not watching, and liking and not liking? So a lot of different places, and each of these pieces of data will likely arrive in different ways. It could be that we have telemetry data arriving via a Kafka cluster on a set of different topics, and therefore we may want to use the MongoDB Kafka connector as a way of ingesting that data into the database. It could be that it's coming directly through a set of microservices. A user is creating a new account, for example. So that could well come directly through a microservice which is interacting with one of MongoDB's native drivers. And it could be existing systems. It could be that there are files and other databases out there, and we need to be looking at using ETL or CDC tooling in order to do that. And most of these tools now have native support for MongoDB. But what is clear is that the recommendations engines are very much one of the key differentiators for these platforms. So we can expect the variety of data and the different data sources to evolve rapidly over time. So it's critical to ensure that we can easily ingest new forms of data as the needs of the model dictates, without the database simply getting in the way. So having got the data though, how do we use it? We can't just take any data that we ingest and then insert that directly into some sort of machine learning model. You have, for example, as the example on the screen here, you maybe have textual data. This is taken directly from one of our the MFlix sample data set, which you can load directly into Atlas if you want to play with it. It's quite a good data set. But if I'm looking at genre, for example, I can't plug adventure straight into a machine learning model. Machine learning models are mathematical. So there needs to be some translation done to make that data into a form that can be used by a model. And that's really where the feature engineering piece is coming in. So within MongoDB, we have obviously the aggregation pipeline. If anyone is not familiar with that, it's effectively we can take some data, and then you can issue queries that are very much analogous to a Unix pipeline to go and process that data. And there's some pretty sophisticated operators that are available in there now. Lots of data operators, mathematical operators, other things that are lending themselves to how you can use this to implement standard feature engineering algorithms. Standardization, normalization, binning, all of these can be implemented directly within the aggregation framework, and I'm going to show you an example of that coming up in just a moment. So let's take an example here of how you would do this. So this is again using my favorite MFlix data set. I'm going to look just here at runtime. We've assumed that runtime has some sort of predictive value for the sake of this explanation. So first of all, I'm going to use MongoDB Compass. I'm going to take a look at what are the properties of runtime within my collection. And what I can see here is that most of the time this is a fully specified integer, which is good. But you can see to the right-hand side there, where the U is, that's just truncated for undefined, there are a small number of moves for which we don't have a runtime specified. So if I try and push that into one of my models, weird things are going to happen. So there's some processing that's going to be required in order to deal with that. But if I look at Compass as well, what I can also see is that it's very much a normally distributed, as you might expect, set of data. There are some outliers at both ends of the spectrum, but the lion's share is clustered around that sort of hour to 2 hour mark in the middle. So what can we do here? So first of all, I can use the aggregation framework to calculate a few input variables here. I could take this as calculating the mean, the max, standard deviation, the average. I could persist this to a collection if I wanted to use it for an incremental calculation, but for now, I'm just going to assume that we can do this all in memory. Next, I'm going to deal with those, because of those movies for which there was no runtime specified. As we know that there was only a very small amount of them, I'm simply going to remove them and ignore them for the purposes of this. So simple exclusion of anything where a runtime isn't present. Next, I'm going to calculate the standardization score. Doesn't really matter about the details of how we do that, but it's a standardized feature engineering algorithm to do that, making use of the standard deviation and a couple of other functions as well. And then we're going to calculate a normalized value for that as well. But then at the end, what I'm going to do is I'm going to use the $out operator to persist this directly into a new collection inside of MongoDB. Now, in this case, I'm just persisting it to a new collection. I could have used $out and persisted directly into an S3 bucket inside of AWS. If this was an incremental operator, I could have used $merge to actually merge this with existing results that I've already got. But the key thing is that what I'm doing is I'm materializing the output from this in such a form that it can then be consumed by my MLOps platform. So just to show you what this does, in terms of the output, I've took the first few results from that. You can see that we now have a bunch of numerical data which falls fully normalized and falling within sort of the expected bounds. So what next? Now that I've got my data into the system, I've done some transformation on that data to make it usable by a model. Now I need to train a model. So how does MongoDB play in this? So let's assume here that I've got inside the dotted box on the screen, we've got a 5-node MongoDB cluster. We've got a bunch of nodes which I've labeled for transactional nodes, and I've got a couple of nodes which I've created specifically for the purposes of running analytical queries. Now, I may have specified these analytical nodes to be slightly different in terms of their CPU and memory footprints, for example. You can do that with asymmetric nodes. I have data which is going out from my transactional nodes using online archive to persist that into cloud object storage inside of Atlas Data Lake. And this means that I can address large volumes of data without needing an enormous MongoDB cluster, which is obviously quite costly to run. So we can get the best of both worlds there by having some of our data live and some of it in a colder storage. Then I'm going to effectively use Atlas Data Federation. So a data federation is going to connect to, on one hand, to one of our analytical nodes inside of my live MongoDB cluster. It's also going to connect to our cloud object storage so that I have one federated endpoint, which I can then use with the Spark connector to get all of that data that I've collected into my MLOps platform, which I can then use for model training purposes. So once I've done that model training, I then need to be able to deal with that real-time aspect. How do I now, having got a trained model, react to something that says, generate me up-to-date recommendations based on something that I'm doing? So if I start with an event, I'm going to assume that the event, for the sake of the illustration, is landing on a Kafka topic. So I'm going to use the Kafka connector to ingest that data directly into my operational data store inside of Atlas. And then we're going to have a change stream, which is listening for changes to a given collection. And then when that change stream triggers, that's then going to push data again across to the MLOps platform, again using the MongoDB Spark connector in order to do that. The recommendations will get generated from within that platform, and they can then push that back into the MongoDB data store, where it can then be made available for microservices to go and query and consume to present to the front end. So, to summarize, hopefully, what you can taking away from this is that there is a way to use the features of the MongoDB data platform to simplify the architecture in order to deliver this sort of functionality. In doing that, you can be more agile, particularly when it comes to the recommendations engines, where you really need to be evolving those things rapidly in line with the needs of the organization. Operationally, there are obviously where there are fewer moving parts, fewer technologies, much less ETL, different copies of the data. Operationally, it becomes much easier in order to work. And then that leads to hopefully an increase in productivity for the development staff who are tasked with building this. Now, I want to leave you with a couple of takeaways. There is a bunch of resources available on the MongoDB website that go into a lot of this in a whole bunch of detail. Some blog posts, and there's some videos as well, so definitely worth taking a look if you're interested in reading a bit more on this. And with that, I'm aware that I am the sole person standing between you guys and a beer which start at 4:50, which I think is probably beyond now. So with that, thank you very much. And if you would like to leave some feedback, it'd be really great if you could, to help us to improve going forwards. Thanks very much.